Hello all, welcome to the next lecture of electromagnetic theory and transmission lines. In the previous lecture, we have discussed about the general solution of a transmission line where we derived the expressions for voltage and current. In today's lecture, we will be discussing the topic which is related to the secondary constants of a transmission line. We already know that for a transmission line, there are parameters like resistance, inductance, capacitance, and conductance, which are called as the primary constants or the physical constants of a transmission line. So, all these parameters are useful for us in knowing the information about the behavior of the transmission line. But in practice, in general, so it might be more convenient to express the transmission line characteristics, or to understand the characteristics of the transmission line, we use certain parameters which will be helpful for understanding the behavior. Okay, so in general, these parameters, we call them as the secondary constant or the secondary parameters. So that are generally defined for any network or any transmission, any line that is used for transmitting the signals. So what are these secondary constants? Let us quickly have a look, right? And let us derive the relation for these secondary constants in terms of the primary constants. So let us quickly start the topic: secondary constants of a transmission line. As I said, these are the constants that are helpful for understanding the propagation of waves inside the transmission lines, which are more convenient when compared to the primary constants. Okay, so these constants do not exist physically. Physically, we cannot see them, or we cannot measure them. But these are the constants that are calculated from the primary. That's why we call them as secondary constants. But these constants, right, really help us in understanding the behavior of the transmission line more than the primary constants. Okay, so the two secondary constants that are very much useful for us are: one is the propagation constant and the other is characteristic impedance. So first, let me define what is a propagation constant. Okay, so in general, if I take any network, if I take any network. So first, let us define it. So if I consider any network, right? So for any network, if Is is the sending current and IR is the receiving current. Okay, so if Is is the sending current and IR is the receiving current of this network, or any transmission line also for that matter. So if Is is the sending current at the source end and IR is the receiving current at the receiving end, okay, then the ratio, the natural logarithm of the ratio of source current to the receiving current is what we call it as the propagation constant gamma. Okay, propagation constant gamma is the natural logarithm of the ratio of sending end current to the receiving end current. Okay, so we can also write this as e power gamma is equal to Is by IR. Okay, so this basically represents what is the ratio, or what is the amount of current received to the current sent. Okay, send current to the source end current to the receiving end current. Okay, so this generally, right, because this is the input by output. So if there is a ratio of output by input, we call it as gain, right? But here we are talking about input by output, which represents attenuation. Okay, because the transmission line doesn't do anything, right? Always the input will be more than the output. Okay, that is what it is actually. Okay, Is value will be more than IR. Okay, so therefore we write the ratio like this. So the propagation constant of a transmission line or of any network can be defined as the ratio of, right, source end to the current to the receiving end current. Okay, to the natural logarithm of Is by IR, where Is is the source end current and IR is the receiving current. Okay, so of a transmission line or of a network. Okay, so this is the thing. Now what does this tell me, right? So in generally Is is the source end current, which is a complex quantity. IR is also a complex quantity. So therefore this gamma is a complex quantity. Okay, this gamma is a complex quantity, and it will tell me, right, generally, how can I define the propagation, or what it tells me? It tells me, right, it tells me what this network or transmission line is doing on the signal when the signal is propagating through it. Okay, that's why you named it as propagation constant. Okay, so this constant tells us, this constant gamma tells us what is the impact or what is the effect of this transmission line or the network on the signal that is traveling through it. Okay, so generally by knowing the value of gamma, we will be able to determine, or we will be able to tell what is the impact of the right network or a transmission line on the applied input. Okay, so that is whenever the signal is propagating through it, what changes happen, right? Or how the network or the transmission line will change the signal. That's what it is going to tell, right? And in general, this gamma value is a complex quantity. Gamma is a complex quantity. So we express it as gamma is equal to alpha plus j beta, where alpha, right, which represents the magnitude of the gamma. Alpha represents the magnitude of gamma, right? So magnitude of gamma. So this alpha is another constant which we call it as the attenuation constant. Okay, so it represents what is the amount of attenuation that is going to happen whenever the signal is propagating through the network or through the transmission line. So gamma represents, right, alpha represents attenuation, the magnitude part of the gamma. Okay, and the phase angle part of the gamma, which we take it as the phase constant beta. So beta is the phase constant. So beta represents what is the phase delay, or what is the lag, or what is the delay, or what is the phase shift that is going to happen whenever the signal is propagating through the network. Okay, so that is right here. The 2 points are clear. Whenever the signal is propagating through the transmission line or through the network, there are two things that can happen. One is it can get attenuated. The amplitude of the signal gets reduced. Second is it's get phase shifted. Okay, so what is the amount of attenuation that is going to happen whenever the signal propagates through the network? That is given by the constant called as alpha, which is the attenuation constant. Second, what is the amount of signal phase shift that is going to happen, or what is the amount of phase shift that a signal undergoes when it is propagating through the network? That is given by a constant called as beta. Okay, so this combined together we get the propagation constant gamma. Okay, so gamma represents a propagation constant which tells me what happens to the signal whenever it is propagating through a transmission line or through a network. Okay, so in general it is a complex quantity. It has a combination of two factors, alpha and beta. Okay, yeah. So this is the definition of gamma. I think if you remember properly, so when we derived the expression for the general solution, the voltage and current, right, we got the expression for gamma also, right? So the gamma for a transmission line can be given as, so I think we remember, if we remember properly, so right, gamma square we assumed it as a constant which is equal to r plus j omega l plus g plus j omega c. We can derive this also, right? Not a big deal again, but it is already given in the previous video. We can go and watch that video. So gamma square is equal to, we got it as r plus j omega l into g plus j omega c. So therefore gamma is equal to root of r plus j omega l into g plus j omega c. So this is the expression for gamma for case of a transmission line. Okay, yeah. But we know that gamma is having two quantities, alpha plus j beta. So alpha plus j beta is equal to r plus j omega l into g plus j omega c. So let us find out the values of alpha and beta as well. Okay, so gamma we have already derived here. We got the expression here. So let us derive the expression for right, alpha and beta. Okay, as well. Yeah. So for doing this, yeah, let me start with this general. Yeah. So again, I will take the same expression. Gamma is equal to root of r plus j omega l into g plus j omega c. Yeah. From this, gamma is equal to, so let us multiply these two and write it as a common vector, a common term. So the real part is we'll get rg minus omega square LC. Yes, real part of the 2. And the imaginary part is j into omega. J omega will be common. So this will be RC plus GL. Okay, RC plus GL. Yeah. So when I multiply and I take out the real and imaginary parts, I will get something like this. This is the expression for gamma. Right now, as just as I told you, gamma is nothing but alpha plus j beta. So alpha plus j beta is equal to, right, this same term again, Rg minus omega square Lc plus j into omega into Rc plus Gl. Okay, right. Now let us take the magnitude of this and magnitude of this. Okay, so this is a complex quantity. This is also a complex quantity. So taking magnitude of both the terms. Okay, so comparing the magnitude part of these terms. So here the magnitude part is a plus jb. The magnitude will be root of alpha square plus beta square is equal to. So again the square will be as it is, right? Now take the magnitude of this. So again I will get a square root. So this will be rg minus omega square lc whole square plus, right, omega square into rc plus lg whole square. Okay, yeah, so this is the magnitude part of this and this is the magnitude part of this. Okay, yeah, so simple thing that we discussed, right? Yeah. Now, taking square on both sides, squaring it on both sides. So we get alpha square plus beta square is equal to. So one root will get cancelled. So I'll have the remaining thing as Rg minus omega square Lc whole square plus omega square into Rc plus Lg whole square. Okay. Yeah, so this is the expression for alpha square plus beta square. Let that be equation 1. Okay, yeah. So I have started with gamma. Gamma is this. So gamma can be written as alpha plus j beta. Now I am taking the magnitude on both sides. Magnitude of this is root of alpha square plus beta square, and magnitude of this is root of again this thing. Okay, so squared on both sides, I got like this. Yeah. So let this be equation 1. So put that aside. Okay. So let me put that aside. Okay. Let us write that equation here. So alpha square plus beta square is equal to root of Rg minus omega square Lc whole square plus omega square into, right, Rc plus Lg. Okay. So this is equation 1. We'll put it aside. Okay. Yeah, whole square. Okay. Now, right, let us continue with the derivation. So again, I'll consider gamma is equal to, so again, I'll start from this. Gamma is equal to, right, r plus j omega l into g plus j omega c. Okay, gamma is equal to r plus j omega l into g plus j omega c. Right, correct? Okay. Now, here, so gamma is nothing but alpha plus j beta. So gamma is equal to alpha plus j beta. So this is equal to root of r plus j omega l into g plus j omega c. Okay, right. Now what I do is I'll square on both sides. Okay, I'll square on both sides. So this will be alpha plus j beta whole square is equal to, so squaring, I'll remove the square root, I'll get the cancel. Square root get cancelled, so I'll get something like this. Okay, so alpha plus j beta whole square is equal to r plus j omega l into g plus j omega c. Okay, right. Now what I do is, so let us expand this as a plus b whole square. So this will be alpha square, okay, plus j beta whole square plus 2 alpha j beta is equal to, so let us expand this also, real and imaginary part. So real part will be Rg minus omega square Lc plus imaginary part will be j omega Rc plus Lg. Okay, yeah. So this is what I will get. Yeah. So now this is nothing but alpha square minus beta square. J square is minus 1. So alpha square minus beta square plus 2 alpha j beta is equal to same thing Rg minus omega square Lc plus j omega into Rc plus Lg. Okay. So this is what I get. Okay. Right. Now from this, right, we can see that this has real part, imaginary part. This is also having real part and imaginary part. So when both these are to be same, so real and imaginary parts are also be to same, so we can compare the real and imaginary parts on both sides. So here I'll compare the real part of this. So alpha square minus beta square is equal to rg minus omega square lc. Okay, so comparing, right, real parts on both sides, comparing real terms, real parts on both sides. Okay, so when I do that, I'll get alpha square minus beta square is equal to, right, rg minus omega square lc. So let this be equation 2. Okay, let this be equation 2, right? Okay, so simple. I have started with gamma is equal to r plus j omega l into g plus j omega c. So from that, alpha plus j beta is equal to r plus j omega l into g plus j omega c. So squaring on both sides, we get something like this. So I have expanded this. Okay, expanded this. All right, I got the term like this. Now I'm comparing the, right, real parts on both the sides. So I get the expression. Okay, yeah. So all right, we got the equation 1, right, and equation 2. Now when we add these two expressions, okay, so let us add equation 1 and equation 2. So adding equation 1 and equation 2. So alpha square plus beta square, alpha square minus beta square. So we get 2 alpha square, okay, is equal to, so sum of these, right, this will be equal to rg minus omega square lc plus omega square l rc plus lg whole square. Yeah, this is the first term, plus, right, what is the term here, rg minus omega square lc. Okay, so this is what I get when I add these two, right, when I add these two expressions. Beta square gets cancelled, so alpha square plus alpha square is 2 alpha square. So I'll get something like this. Now from this, alpha will be equal to, right, this will be as, so alpha means, so I have to take under root, a bigger under root, right? So okay, the term will be rg minus omega square lc plus omega square into rc plus lg whole square. So under root up to this, plus this term will be rg minus omega square lc, okay, divided by, that's what I get. Okay, so this is the expression for alpha. Expression for alpha is this. Okay, so the expression for alpha will be like this. So this is, I think you have understood. Okay, so right, when I write like this, I will get something like this. Alpha is equal to root of, right, root of rg minus omega square lc plus omega square into like this. Yeah. Similarly, when I subtract the equation 1 and 2, okay, if I subtract the equation 1 and 2, I will get, right, subtracting the equation 1 and 2, right, when I subtract the equation 1 and 2, so I will get beta value, right, which will be same as that of above case, okay, except, right, we will get a sub minus here, or g minus omega square lc plus omega square into rc plus lg whole square, okay, minus rg minus omega square lc, right, divided by, so everything is same except, here, instead of plus I get minus. Okay, so right, remaining all the terms are same. Okay, so this is the propagation constant, right, and attenuation constant and phase constant. Okay, so alpha represents the amount of attenuation that a wave undergoes when it is propagating through the transmission line. Beta represents, right, the amount of phase shift that a wave undergoes whenever a signal undergoes whenever it is propagating through the transmission line. So in all, propagation constant will tell you what is going to happen when a signal is propagating, when the signal is propagating through the transmission line. Okay, so I hope you have understood. Now we have another right, secondary constant, which is the characteristic impedance. Yeah, let us see that also. Yeah, so characteristic impedance is generally defined for a network like this. So whenever a network, right, if a network is shorted or is terminated by an infinite series of networks, okay, so if, right, if a network is terminated by an infinite series of networks, then the input impedance of this network, right, the input impedance measured at this network is called as the characteristic impedance of the network. Okay, so whenever there is an infinite series of networks, or whenever you have a network terminated, this network, so this network, whenever this network is terminated by an infinite series of similar networks, then the input impedance measured at the first network is called as the characteristic impedance. Okay, so characteristic impedance of a transmission line or of a network is the input impedance of the network. Okay, measure, right, input impedance of the network, right, measured whenever the network is terminated by an infinite series of impedances, or infinite series of networks. Okay, or you can say that whenever the length of a network or a transmission line is large, then the then the impedance measured at the input terminals will be equal to the characteristic impedance, or is called as the characteristic impedance. Okay, so characteristic impedance of a transmission line or of a network is the input impedance of the network or the transmission line when the network or the line is terminated by an infinite series of networks. Okay, or you can say is of infinite length. Okay, so whenever this happens, then such an impedance is what we call it as the input impedance, is called as the characteristic impedance, right? So generally, why do you call this as a characteristic impedance means, so in general, the impedance, right? For example, if I have an infinite length of the transmission line, then if I cut this transmission line at this part, right, and measure the input impedance, then this will also be equal to, or will also be called as the Z naught itself. Okay, that value will also be because infinity minus something will not make much difference. Okay, so this will also be defined as Z naught itself. Okay, and if I cut it here and measure the input impedance, then this will also be equal to Z naught. Okay, so this implies that the value of Z naught will remain, the value of the characteristic impedance will remain same throughout the entire length of the line. Okay, so therefore that's what we say that, right. Okay, the characteristic impedance will be the impedance measured at any point. It will remain same on an infinite length of the, or very long wire transmission lines. Okay, so that is why we say it as characteristic impedance, because it is the impedance that is characterizing this transmission line. Okay, yeah. So let us see how we can measure this characteristic impedance in a transmission line. So for this, I will take the help of the general solution again. So in general solution, we have written the expression for V of x and I of x. So V of x is equal to V plus into e power minus gamma x plus, right, V minus into e power minus gamma x, sorry, e power gamma x. So this is what we got. Similarly, I of x is also obtained. I of x is equal to I plus into e power minus gamma x plus I minus into e power gamma x. Okay, so these are the solutions that we got. Okay, right. Now, from this, okay, let us take these solutions, right, and let us put them, right, back into the equations that we derived. Okay, we got an equation which is dv by dx is equal to, so right, I think you remember this equation. So if not, go back to the previous video. So dv by dx is equal to r plus j omega l into I. This is, I think, what we got expression. Okay, so here v means v of x and I means I of x. Okay, yeah. So let us put those two terms here. So d by dx of vx, v of x is nothing but v plus into e power minus gamma x plus v minus into e power gamma x is equal to minus r plus j omega l into I is I plus into e power minus gamma x plus I minus into e power gamma x. Okay, so this is the expression, right, after substituting the solution. Okay, yeah, so this is what I got. Okay, yeah, from this, yeah, so from this, yeah, so let us differentiate this. So this will be v plus into differentiation of e power minus gamma x Okay, so gamma is a constant, so I'll write minus gamma into e power minus gamma x. Okay, and differentiation of this v minus into e power gamma into e power minus gamma x. Okay, so same thing that I will get is equal to, right, minus r plus j omega l into, right. So this will be as it is. There is no differentiation here. Okay, so what I get is like this. Okay, yeah, so just differentiated, right? What I have done is I have differentiated this expression. So d by dx of e power minus gamma x is minus gamma into e power minus gamma x, and this is gamma into e power minus x. Okay, right now. Now this quantity has to be equal to this quantity. Okay, so right here I have two components, here also I have two components. Okay, so if this quantity has to be equal to this quantity, then the individual components, then the individual forward and reverse components must be same. Okay, must be equated. Okay, so then only it is possible, right? So therefore, right, what I can write is, so therefore what I can write is comparing this term and this term. Okay, so I'm comparing that. So v plus into minus gamma, or we can write this as minus v plus into gamma into e power minus gamma x is equal to minus r plus j omega l into I plus into e power minus gamma x. Okay, comparing this quantity and this quantity, the forward components. Okay, so this is a forward component, this is a reverse component. Similarly here, this is the forward component and this is the reverse component. Okay, so if this total term has to be equal to each other, then the individual forward and reverse components must be same. So using that I am doing this. Okay, yeah, so from this e power gamma x and e power minus gamma x gets cancelled. Okay, so we get v plus by I plus, v plus by I plus is equal to minus minus also gets cancelled. So r plus j omega l divided by gamma. Okay, so that's what I get, right? V plus by I plus is equal to r plus j omega l by gamma. Okay, so right, we know that V is voltage, I is current. So ratio of voltage to current is generally impedance. Okay, so what is this impedance? The impedance at any point. Okay, so that is generally, right. So because yeah, we have r j omega. Yeah, yeah. Okay, yeah. So let us continue this. So V plus by I plus is equal to R plus j omega L divided by gamma can be written as root of R plus j omega L into G plus j omega C. Okay, so this is equal to R plus j omega L, right? One gets cancelled, so I'll get root of R plus j omega L by, okay, by G plus j omega C. Okay, so this is the expression for V plus by I plus, correct? So this is the expression that I get. V plus by I plus is equal to, right, R plus j omega L, right, by G plus j omega C. Right, from this we can observe, or we can clearly see that, right. So whatever the the ratio that we got, right, this ratio V by I is impedance. Okay, so it generally represent a Z value. Okay, it is representing a Z value. Now what is this Z? So if you see here, all the terms that we have are the physical parameters. Okay, so this impedance that you get is a right characteristic of this primary constants. So therefore we take this impedance as the characteristic impedance represented by Z naught. Okay, so Z naught is equal to root of R plus j omega L by G plus j omega C. So here, right, this impedance, right, we generally voltage by current represents an impedance, right, and here the impedance that you're talking is the right is a function of primary constants. So it is right characterizing your transmission line. So therefore we say that this impedance is nothing but the characteristic impedance of the network. Okay, so therefore we take this as Z naught. Okay, yeah, similarly by comparing the negative terms also, so on the negative part also, if I do the same thing, I'll get the same thing. Only thing is right, I'll get a negative. Okay, so that therefore I can write that V plus by I plus is equal to Z naught. Okay, so from this V plus by I plus is equal to Z naught, right, and minus by I minus will be taken as minus Z naught. Yeah, remember these two things. Okay, so in the same way, if you compare, you will just get a negative sign. Okay, so V plus by I plus we take it as Z naught, and V minus by I minus will be taken as minus Z naught. Okay, V minus by I minus will be taken as minus Z naught. So this is another expression that you get by comparing the backward components. We compare the forward components. If you compare the backward components, you will get this expression. Okay, so right, Z naught is equal to root of R plus j omega L by G plus j omega. See, this is the characteristic impedance of the transmission line. Okay, yeah, so with this we get to the conclusion of the secondary constants. Okay, so the secondary, we have two secondary constants. One is a propagation constant, another is the right characteristic impedance. These two secondary constants help us in understanding the behavior of the transmission line more effectively. Okay, so rather than the primary constants. Okay, so these are not physically existing, we calculate them from the primary constant itself, but when we calculate them from primary constants, this information, the value of gamma and the value of Z naught, will help us in understanding the characteristics of the transmission line more effectively. Okay, so that is why we prefer them. Okay, yeah, so thank you.